Okay, so I'm going to record this again, so hopefully we'll have sound on it this time. So you all know what wind tunnel you've been using. You use it twice now, once for your Airfoil experiment and once for your boundary layer experiment. So the next two tutorials are 7 and 8. One is to simulate the flow over an Airfoil, and the other one is to simulate the boundary layer problem. This one we're going to use 2D, and we're going to use Fluent again. So much of this you've seen already in the tutorials in the intermediate part of the course. There is an online, another version, which is different to this, but it's also interesting to follow there on the Cornell website. So with this, the key step here is getting the geometry of the foil into Fluent, and we're going to do that in Design Modeler. I'm going to show you how to do that. So, but apart from that, pretty much we're going to follow very similar steps to what we did previously, where we're going to mesh it up in the desktop meshing. We're going to work with Fluent. We're going to use the turbulence model again, like we did in the 5th tutorial with the turbulent flow of a backward-facing step. We're going to modify the fluid properties so they match the ones that match your experiment data. We're going to apply boundary conditions, post-process in CFD post, which is the ANSYS inherent CFD post-processor. One additional step we're going to do here is create a parameter set, which is a construction in ANSYS which allows you to essentially do a design of experiments where you can modify parameters to drive the analysis for specific outputs. And then we're going to compare the models to the experimental data. Well, when I say we, I mean you, because that's part of your validation. So you know this from your C1 assignment. Your foil is located in the wind tunnel test section, which is roughly 600 millimeters long by 300 millimeters high by 300 millimeters wide. It's a NACA foil, and it's a 0012 foil. Now, the chord length of this is 150 millimeters, and you've got tap locations all around it in the experiment, as you know. You varied the airflow velocities between 10 and 30 meters per second, actually. So you know from your first assignment that the Reynolds numbers varied from 100,000 at the 10 meters per second up to 300,000 for your 30 meter per second flow rates. You were asked to determine lift from your drag lift data. So you had the forces, the lift forces and the drag forces that you generated. At 30 meters per second, you were roughly, your peak lift force was about 29 or 30 newtons, and you had a stall angle, which was you were asked to compare to the data from Gregory et al. Or any other references which you found that were relevant, which was fine as well. And from that, you can see that as your there is a change in the stall angle, and also a change in the peak lift. You can see in the lift coefficient, and roughly your trends should have been going in the right direction, so that your lift angle, your stall angle, sorry, keeps on increasing slightly as your flow rates go up, but also your peak lift also goes up. Okay, so let's have a look at the opening up the tutorial 7. So if you double click on ANSYS. Now hopefully this copied across okay this morning. Tutorial 9 didn't, but I had problems saving tutorial 9, but tutorial 7 seems to have gone here. So let's have a look at the first analysis A there. We've called it velocity equals 10 and angle of attack equals 8. Okay, so the what you can do is you can go to the airfoils.com website, and you can actually pull out from thousands of different foil shapes, and you can select one of the NACA 0012 foil sections, and you can modify that so that you actually make sure your chord length. So these airfoil shapes are scalable. There are a number of different variants of the NACA 0012 foil, and they're not, so you can choose, if you choose to change the chord length, that doesn't make any difference to the profile of the foil. It's just scalable in terms of that. The width and but you can set those, and you can export that then as a CSV file. Okay, you have to manipulate the CSV file actually a bit to be able to get it into ANSYS. So you need to have a format which has this pound sign, and you put in a title, and then you have to each of the coordinates is put into a group, and then you number the points. There's relatively little manipulation. You can do it all in Excel, but then it has to be exported back to a text file. And when you look at the text file, and I'm only telling you this just for in any reason you want to actually go ahead and change the foil. You can put a camber in it, or you want to create two foils. So if you had a dual wing system, you can do that as well. You can see that it's all, the Z chord is all 0, and then the X chord varies from the 150 mil, which is the chord length, so it's right at the back, and then it goes all the way around. So when you're manipulating those, the important thing is to remember is that you need to have the very last point here defined as well, and that doesn't often come off from the Airfoils tool. But that's only if you want to get into the nitty-gritty of actually changing the foil shape. Otherwise, it's given to you. You can download it, already manipulated within Excel. And the next stage is then to how do we get that curve in? Okay, so you insert a 3D curve there, and then you actually tell it you can import the coordinate file from here. You can find it wherever you've got it located, and you've got to make sure that you get your coordinates right, the units, and you add the material. So if we suppress all of those below, what we've got is a curve. The curve has come in. All that does is create a curve. And what we need to do is we need to convert that curve now into surface. All right. So in that case, we go concept, surfaces from edges, and two things, because first of all, we've also put a rectangle around the outside, and we've got we need to take away the two surfaces. So at the moment defined here, we've actually got two surfaces. We've got the rectangle, which is going to represent the test section, and we've got the surface that was created from the foil itself. So what we are going to put in here as well is a rotation. All right, but to do that, we need to create a plane right on the tip, right at the location where the rotation takes place. So you've got to give that rotation an axis, which is going to be running through the middle of the foil. And that allows us to set a rotation, which in this case we're going to call -8. So we've still got two surfaces, one representing the foil, one representing the test section. We've also introduced a rotation which allows us to rotate the rotate the foil at any angle we want. So now what we need to do is we're only interested in the flow over the foil. We're not interested in what happens inside the area of the foil. So we need to subtract the two from the other. And we'll use that using a Boolean. Well, that allows us to subtract the foil area from the test sectional area. And that leaves us with a foil pointing down at 8 degrees, and that's our 8-degree angle of attack, which we're going to simulate for the time being. Now, when we brought in and created a line representing the outline of the foil, we created a line body. We don't need that in the analysis, so you can right-click and suppress it, and that means it doesn't come through into Fluent in any way whatsoever. That's the construction of the geometry. Let's have a look at what we do with the mesh. Okay. Wait for that to update. So I line it up to the z-axis. So what we see is that the geometry is brought in a single surface, which consists of the fluid side, the fluid domain of the flow around the foil. Okay, so let's see what, and in this particular case, because we've got a slightly more complicated geometry than we had before, for example, in the backward-facing step or the flow in the channel, we're not going to spend so much time worrying about how we're going to improve the mesh. Having said that, we are going to introduce a refinement around the area of the foil. But we're quite happy to keep triangle elements. Now, if you remember what I said in the previous tutorials in the CFT, that avoiding triangle elements where possible in flow was beneficial to the simulation. So a couple of things to note about the mesh. First of all, in this instance, we've got the advanced size function on the mesh set to proximity and curvature, which means that the mesh will adapt itself around areas of high curvature and propagate away. The refinement that we've generated has allowed us to cluster up the elements, particularly in areas where we know there's going to be quite high changes in velocity around the area of the foil. Particular area of problem is the back of the mesh, so back of the foil, sorry. So that's an area where this particular method of refinement has clustered the elements in a way which don't look too bad, actually. Right, so as with the previous flow, we need to let Fluent know where our boundary conditions are. So I've created 3 named sections. One is our inlet, same way as before, where to create that we select the line selection tool, we select the line, right click, and then create named section there, and then you give it the name inlet, and that creates this inlet named section. We do the same for the outlet, where the flow is going to go out, but in this case what we're interested in, whereas before, when we had a section of wall where we know that Fluent is going to apply a boundary condition, the no slip boundary condition, i.e. the velocities are all 0, and we didn't particularly care what was happening at those walls. Now we are very interested in what's happening at the wall, because they are going to give us the information that we need to extract the lift and drag forces. So we're going to call that foil wall, and we do that in exactly the same way. We use the line selection tool, we select the boundary of the edge, and you see it go green there, right click, create name section, and then I've called it foil wall. And you see the foil wall's been selected. And that's all we need to do. We've got our mesh, we've got our named boundary conditions ready to go. So we can close the meshing tool. It hasn't updated, it thinks we've done some changes, so we can right click and then update. Right, so now we're going to open Fluent, and we're going to keep double precision on, which is what we've worked in. So this is very, very similar to all the other simulations we've done with Fluent so far. So Nothing particularly astounding coming in. First thing to check, does the mesh look like the one we just created? Sometimes Fluent will get confused and might try to use a previous mesh. I think as far as I can tell, that is exactly the same ones we had. You can see the blue inlet boundary there, so it's identified as an inlet boundary condition. The exit boundary, which is the red on the right-hand side. And then you can see also that around the foil, you've got a white boundary. All white boundaries in Fluent are wall-type boundaries where the velocity is going to be 0. So, as before, in terms of the model itself, we're going to keep those exact same default. So we're using a steady solution, pressure-based type solver, and just to note that it's a 2D planar space. We're not bothered about the influence of gravity in this particular case. For the models, the default one is normally laminar, but we've selected the K epsilon in the same way as we did with tutorial 5 with the turbulence model. There's no need to change anything else, particularly at this point, and just leave the default options there for the model. Materials for this one, we've used the default material properties or fluid flow properties, so density and viscosity. We've used the default ones from Fluent. Now, when you did your experiment, E1, a few weeks ago, you would have had different pressure and atmospheric temperatures. So I don't know how much difference it would make exactly, but to be as precise as possible, you'd want to actually put in your density and viscosity based upon some calculation of those based on tables or something. So I haven't done that, but you guys would have to do that for your validation, is make sure you're using the right density and viscosity. Nothing else much to look at, except now we're going to look at the boundary conditions, much the same way as we always have done. First thing to note that we've actually got 5 boundary conditions defined here, although strictly speaking, the interior surface body is not a boundary condition. But the ones that matter, the foil wall in white is a wall condition, so we know that on the wall we're going to get a stationary wall with no slip. We've got the inlet, we've got the outlet in red, and then we've got some walls defined by the top and the bottom parts of the test section. For the inlet boundary condition, we're going to select a velocity of 10 for the time being. In much the same way as we did for the previous tutorial, we're going to use intensity and hydraulic diameter, because we know the diameter. So for our boundary conditions for inlet for the turbulence model, intensity and hydraulic diameter, turbulence intensity of 5%, and the hydraulic diameter we're going to pick to be the same diameter as the test section inlet, which is 0.3. For the outlet, we're going to have an outflow, which means that we don't really need to define very much at all. And all that's saying is that mass is conserved at the outlet, and there's no weighting on the flow. It's just what comes in is what goes out. The simplest boundary condition you can have. So I think that covers the geometry, the meshing, the boundary conditions there. So we can actually just go and run it. Now, before we run anything, we have to initialize it or prep the solution on the interior nodes. So you can hit initialize. You can see it does it very quickly. 10 quick iterations. That means there's now some sort of starting value for pressures and for velocities and everything it's solving for within the mesh. That will make it run a bit faster. So we're going to select 500 iterations as the number of iterations for the solution. And if we hit run, we can see the usual scaled residuals being plotted up, and we can see, as usual, for a two-dimensional problem with the turbulence model, we have 5 sets of residuals, one for the continuity equation, x and y for the momentum equation, and k and epsilon for the k epsilon turbulence model. So I went into a lot of detail about, well, not a lot of detail, a bit of detail about what the turbulence model was last time. That is it in terms of Fluent. So you can close Fluent, and it'll automatically save an instance of your model within Workbench, but remember, Workbench doesn't automatically save itself. So if you want to save this as you're going along, now's the time to hit save. We haven't done many modifications, so it's not a big deal if it breaks down and crashes. But what we're going to do is have a look at the results. There's a bit more work to be done on the results here. Okay, so this has come up with all the stuff that's already been done on this model. But just to remember that this CFD post-processor within ANSYS is inherently a three-dimensional. So that's why what it's done is it's taken our two-dimensional solution from ANSYS and it's given us two planes of symmetry on either side, but all results are replicated on both those planes. And it's perfectly all right. If you look at it, you'll see that they're all identical. So, same way as before, just check geometries come in, it's got the right dimensions. You can plot the mesh if you want to by clicking on the wireframe and showing the surface mesh, or you can disable that so you don't see it. Okay, you can insert contours, vectors, streamlines, and we're going to go through those now. So we'll try to do it in the right order. The first thing we'll do, create a contour. So insert contour. Because we've already got contour 1, it's creating a contour 2. Okay, and here we will pick the location. You can see you've got two these symmetry planes I talk about, which are just artificial constructions of the post-processor. Either one will do. And then if we want to plot the pressure, there you can see your pressure. So that should make more sense now that you've done the experiment. It shows you sort of the positive pressure on the upper part of the foil and the higher pressure on the lower part of the foil. And if you can remember your KPAs, this is roughly the same magnitude, order of magnitude of, well, it's roughly the same size as the KPAs that you were getting from your experiments. So that's good, because we know we've got some sort of validation in our mind from the experiment, from the pressure profiles there. So that's fine. Now, streamlines. Okay, so what I've created here is two sets of streamlines. One which allows me to go a bit finer than the other. That's why there's this plane in here which creates a small rectangle around this area and allows you to release streamlines from within that plane. The reason I've done that is when you start to get to the recirculation point, at the moment we've got the angle of attack at 8, and if you remember from your lift drag curves that you plotted up, it wasn't until you get to about 12 that you start to get a recirculation behind the foil. So at this point what we've got is no real detachment of the flow over the foil, and that's seen in the streamlines. We'll have a look at that later on. You can also plot vectors as well. So in the same way as you can insert vectors, this allows you then you can zoom in and start to have a look at the flow, and you can look down to see whether you're seeing any detachment or recirculation zones or any separation of the boundary layer that runs around the foil. Right, so we are interested, we've got pressure profiles from our experiment. So what we'd like to be able to do is to extract that from our model to be able to ultimately be able to compare pressure profiles with the experimental data. But to do that, we can't just use the, we have to create an instance, a polyline or a line. So let's get rid of the vectors, let's get rid of the wireframe. We have to create this boundary from the geometry somehow. So to do that, you go insert, location, and polyline, call it polyline 2, and the method that we're going to use is a boundary intersection. And we're going to create a boundary intersection of the foil wall with, I think, that one. So let me just look at the first one. Symmetry wall, foil wall, symmetry wall. Okay, it doesn't matter which way around you do it, it'll create it anyway. So what it does there is you've got a boundary which is defined, which has come all the way from the geometry, which is we called it the name section foil wall, and we're going to get that to intersect with the symmetry mesh, and that allows us then to get this polyline. We don't need two, we've already got it there, which that gets the mesh coinciding along those lines and allows us to plot it. So we can then go insert chart. We've got one done, but I'll do a chart 2 anyway. Data series 1, like we did last time, but the location is going to be polyline. And what we're going to plot on this chart is the x-coordinate in the x direction, there, and on the y-axis we're going to plot pressure. So hopefully we'll get the pressure distribution. So that's the pressure distribution for a velocity of 10 meters per second with an angle of attack of 8. And hopefully, from your pressure distributions that you had, you should be able to get a really good match from that, if you should wish to do so. All right? Right, that completes the basic outline for all the other analysis. All we want to do now is we want to change our two experimental independent variables, which was the velocity and the angle of attack. So we can close that. And all I've done here is duplicate that first analysis. Okay? And within each duplicate that I've made, I've changed I've kept the velocity at 10. I didn't want to do creating too many instances of this time, but I've changed the angle of attack. So, if you just go left click there and duplicate, what we'll do is we'll create here an angle of attack of 15, just to show you how to do it. There. We can locate that there, just because we know that's part of our analysis. We've got 8, angle of attack 12, angle of attack 14, angle of attack 15 now. Where was the rotation defined? In which part of the analysis, where did we define the rotation? I'll open it up. In the geometry, if you remember, our fourth function here was a rotation. So for this one, we're going to use, let's have a look at it from the side. You see when the foil first came in, it was at 0. And then we rotated to 8, and now what we're going to do is rotate it down to minus 15. Okay? So if we generate that, we can see now the foil is rotated around that pivot point to 15 degrees. That's all we need to do. We can close that down. We need to update everything else, but we don't necessarily have to go into it. We can update. There we go. And the tick goes to green. That means we've got a mesh for it. Let's have a look in Fluent. And all we're going to do here is just initialize and run it. We don't need to change anything else. The velocity is still 10 meters per second. We're going to keep it at that. We can see that the mesh should be updated so that the angle of attack is now 15 degrees there. Okay, we don't need to change anything in the boundary conditions. All we have to do is initialize and run. So that was the step to change the angle of attack from 8 to 15. I've done the others, 12, 14, etc. But that can get quite repetitive. Copying an analysis, changing one little value, and carrying on. And not only is it repetitive, but it's prone to error. You might by accident have changed something you didn't particularly want to change within the analysis. Okay. All right, so we could post-process the results here. And then we could do each of these independently and have a look at each one of them. And that, again, is also quite repetitive. What you can also do is you can converge all of the results into a single post-processing instance. That allows you to compare all the results at once. The way to do that is if you look down on the individual component systems here, you should be able to see results somewhere. Is it there? Yeah, there we are, results. So you can drag and drop that down, and then you've got a standalone system there where you can drag all the results from all your previous analysis into one place. Okay? So I've already done that for you here. And what you can do is when you've got that single instance results, you click on the solution and you can drag it over so that now you can see we've linked all of the solutions into one single post-processing home. And that saves them to keep on opening up and closing, opening up, closing all the different result sets. And so if you double click on the results bit at the end, see, it allows you to have up to 4 separate analyses in 4 parts of the window. So you can see the angle of attack changing there from 10 to 12 to 14 to 15. And what it allows you to do is you can synchronize the movement in each of those windows so that you can zoom in to any particular part of a feature of interest. So, for example, here, we're going to focus maybe on what's happening to peak pressure as you go up through the angle of attack. And most interestingly, what happens to is there's something that happens during that transition over the stall angle between 14 and 16. You can, in addition to contours, of course, you can look at the streamlines. And when you create streamlines in this instance, you are creating them for all of your meshes. So what you can see there, that as we go through from 8 to 12 to 14 to 16, you can see where and how the recirculation commences along the lower part of the foil, and how that increases, and eventually it's starting to spill off the back of the foil. Okay? With the same method we used before of creating the polyline and identifying the surface of the foil, we're also able to get the pressure distributions. So you can also get your pressure distribution exactly the same way as you had in the experiment for the foil at the different angles of attack. And now you can see in this instance we've also got what we could do is go back to the 3D viewer, look at that, and let's say instead of 12 we're going to look at 15, and instead of 8 there we're going to look at 12. So there we can then see an intermediate stage of the development of the recirculation zone behind the foil. Right, so we're almost at the end of what we do need to do. And I'm going to do this. All of that's quite a little bit repetitive. Yeah, I mean it's great if you want to compare one instance of the simulation with another, like we have done there. We're quite interested in that particular development of the flow around the foil to see what is causing that stall. What are the root causes of that stall? But that is, yeah, as I said, a little bit repetitive. You could repeat all of that just using one single analysis. And this is where the parameter set comes in. So what we'll do with the parameter set is you have to, if we go back to the geometry in the model G there, at the moment we've got, that's just angle of attack 0. Our rotation there, we've defined the angle through which we rotate it as a parameter. So you can't change it anymore within geometry. That gets changed outside the program now. Okay? We can close that. Now, what's the other parameter we want to change? Velocity, yeah? Okay, and where's the velocity? Where do we put the velocity in? Within Fluent, yeah? So, if we go into Fluent, right, we go to boundary conditions, we go to inlet, and we edit it. We can see now that we've got a parameter. Okay? Now, parameters are defined here. You can create parameters. Why can't I do? Hang on. I think I went into the wrong place. So, try again. Okay, sorry, I went in through the wrong place there. If you go through setup to start Fluent, you can see that we could have had it as a constant, which is what we originally had it as. We just set it as 10, and then we had a multiple instances of the same analysis. Or we can create a new input parameter. If you create a new input parameter, all it does is say, right, you've got parameter 2, and you can have that. We've already created that here, so we called it parameter 1. And that means that now that particular instance, that velocity parameter, can be manipulated outside of Fluent, and everything else is left to run. Okay, we could do exactly the same with the turbulence intensity by clicking on a parameter for that. So almost all of the input values that you get in the boundary conditions can be driven by external parameters. But we only need velocity in this instance, so we can close down Fluent, nothing else to do. But when you create parameters within the analysis like that, what it does is it creates this kind of loop called a parameter set, which if you double click on it, this shows you the input parameters for that you can run. And it has a current, which is the one that it will run by default, and then you can create new ones. So if you go down to the bottom of the list, say if we wanted to run this foil at an angle of attack there of minus 25 degrees, there, it's created a minus 25, it's selected a 10 meters per second velocity for parameter 1 here, which is the velocity parameter, and those are input parameters. And what it's going to do is it allows us to have this table, run all of those instances of the analysis, but it doesn't save any of the results. It might only give you results back that you actually want. So we want lift forces and drag forces. I'm going to show you now how we get to those. So input parameters, you have to go into geometry, or you go into meshing. You could define the mesh as an input parameter. So you get a number of divisions, or the size of the refinement. They could be parameters as well. In the results part here, we're going to have output parameters. So what we're interested in is being able to control which independent variables are solved for, but then we also need something coming back for us, and that's the output parameters. Here we're going to create, and the way we do that, and we've seen this before, we're going to use expressions. So just trying to remind myself and make sure I get this right. We're going to create an expression called force X at foil wall. Okay? All you have to do, you enter that text, and that is a script which allows you to, the foil wall is a predefined parameter, a predefined named section, and force X is calculated for you. And you can see that it gives you a preliminary value there when you hit apply. So we need to do that for both the force X and the force Y. So those two things, yeah, tell us that they are, so the force X is the drag, and the force Y is the lift. Okay, and if you right-click on that, yeah, you can make it an input parameter or an output parameter. And we've selected output parameter, which means that if you close the result set there, and you go to the parameter set box back on the workbench, you can see we've got two output parameters defined here. You've got, at the top here, you've got the fluid flow input parameters, you've got your angle of attack, and you've got your velocity, and then you've got below, you've got your output parameters, which is the lift and drag. Okay, so the drag is the x, because that's in the x direction, and here you've got your lift. Remember, this one was for angle of attack of 0, and we can see that we've got a minus number. So it's the same as with the experiment. You've actually got a minus number, but that needs to be inverted to give you the positive lift. When you do that, you can update all design points and walk away from the computer, grab a cup of coffee, and leave Fluent do the work for you, and it'll come back. But remember, you won't have any pictures from that. It won't output pictures. It'll just output literally what you asked it for, which are the output parameters. So you'll have the x force and the y force. And that data, you can select the entire thing. Copy and paste it straight into Excel, and as I said, you're going to have to make these positive. Okay, so let's say, for example, let's take the let's make a graph of so we're going to make x our angle of attack between 0 and 18, and we're going to make y our that wasn't a very clever thing. So we're going to make y, in fact y is that. So this was u equals 10 meters per second there, and that was drag, and that's lift. And we can see that we do have a bit of a blip there. It's probably not as well defined as the experiment, but we do see that there is a stall, and we can do exactly the same for the 20 meter per second. And we can do exactly the same for the 30 meter per second. There. Right, that's great. What's wrong with that? Labels, yeah, there's no labels on it. Now, but what about the actual magnitudes? What sort of magnitude did you have at the 30 meter per second flow rate in terms of the lift forces? Come on. You just had feedback on your assignment, all that. Oh my God, you must know. That was about 30 newtons, yeah? So that one on the left there is newtons. and you've got 100 newtons. Why have we got 100 newtons when it should be about 30? No. All right, okay. So the post-processor that we use to calculate those forces with is working on the basis that the foil is 1 meter wide. So it uses a kind of unit of 1 meter. So that extrusion that the processor, which is 3D, is taking 2D results and it's extruding it by a meter. But in actual fact, our foil was 300 millimeters, so it's about a third. So if you divide that by a third, you get more or less the right answer. Okay, so I think that concludes. I don't think there was much else here in terms of the tutorial. I've shown you how to create parameter sets, the running of the parameter sets. So I'm not going to do it myself now, it'll take forever, so you can do that. But remember to divide the output from the post-processor by 3, or just on the lift. It doesn't apply to drag, it's just the lift, okay? And that's it. That's tutorial 7. So we'll take a break, and we'll get on with tutorial 8.